Hey everybody, big day today. We're going to look at our first actual machine learning algorithm. The algorithm we're going to look at is called K nearest neighbor, and it's one that is simple enough that I think I can ask you guys to try and code it yourselves. So that's what I'm going to do. We're going to code this one ourselves. There will be one other algorithm much later that is also, I think, simple enough that I can ask you to code it yourself. When I say simple enough, I don't mean it's necessarily going to be easy for you to code, but it's certainly more, it's within your reach in a way that the other algorithms we're going to look at are not within your reach, or would, well, they may be within your reach, but they would take a lot more effort to code them properly. So the algorithm is called K nearest neighbor, and there's two main videos here. The first one, the aim in this video is to explain how the K nearest neighbor algorithm works. It's a very simple idea, which, as you probably know by now, doesn't mean it's going to be simple to code, but it is a simple enough idea. And then we are going to, in the next video, we'll look at ways of improving it. So the goal of this video is to maybe even get you writing code. There's no real exercises this week other than work on your implementation of the K nearest neighbor algorithm. So I'm going to try and walk you through in two steps to the K nearest neighbor algorithm and suggest that you actually try and create it yourself sort of now before I even give you the assignment. So let's take a look at the handout. There are two handouts this week. One of them is just called KNN Basics. KNN stands for K nearest neighbor. The K is usually lowercase. We're going to start with nearest neighbor, which is a much simpler version of the algorithm, and then move on to K nearest neighbor. So let me explain to you what this means. So if you take a look at, remember the banknote authentication data that I gave you a scatter plot of. One of the observations you probably all made about this is that the two classes, counterfeit and legal, form like overlapping clusters or neighborhoods. Most people would probably say, if I put a new point out here, they would probably say that point belongs with the other greens around it. And if I put one down here, they would probably say it probably belongs with the other reds that are around it. So what we're kind of doing there is the idea is that we're looking at its close neighborhood to see what labels are in that neighborhood around the new point, and then we're trying to categorize it. I have some sample code here that I'm going to run. What you've got is two things that create data sets. And so I have this create data set function here that creates a really simple data set and returns labels. So it creates an NP array of data and then some labels, and it returns the data and the labels. So if I go data, comma, labels equals create data set, then we've got a data array and a labels array. So this is two-dimensional data. So this is the X and this is the Y. So the first point is at 0.9, 0.8, 1, 1, and so on. And the first two, and this is a related array of labels. This is what your data is going to look like for the machine learning, for the most of the tasks that we're gonna talk about. I have a little whiteboard here where I scribbled some stuff. This is why related arrays are so important. The data you're going to get is going to look like this. You're going to get this data array, which will be a two-dimensional array. Each column is an attribute or a feature of the data. So it's something that we measure, and each row is a data point. So when you index into a two-dimensional array, let me show you here. If I go data 0, that's the first data point in that two-dimensional array. That's the first row, and the label that goes with it, the class label, is A. On the other hand, labels 3 is B, and that goes with data point 3. So these are related arrays, even though one of them is two-dimensional. So item 0 in the data array is the data for that example, and label 0 in the label array is the label for that example. Okay, so that's what you were setting up in the last assignment. So you were setting up arrays of data and related arrays of labels. So that's what this function creates. And I don't know if you can visualize it. Normally I would draw them on a whiteboard, but instead of doing that, I just decided to create. So I'm going to uncomment this code here, which uses matplotlib to create call create dataset to get the data and the labels, and then graphs them. So notice what I've done here is I've scattered the first 2 points, the x locations and the y locations, using red, and the second 2 points using blue. So red is A and blue is B. And then I've added just another point with a different colored marker in there. So if you take a look at that, if I told you that x is either red or blue, which do you think it is? You would probably guess red, because it's closer to the others. And we can sort of quantify that by saying, well, which of the known points, so these are our known points, the reds and the blues, and this is our unknown point, which known point is it closest to when we graph it? And you can see, without computing, we can just see that it's closest to this point right here. So we can say, okay, we'll just take the nearest neighbor, the closest point to x, and whatever that one is, we'll predict that this is the same. So we're going to predict class A, which is red, for point x. If I put another example, I don't know, 0.2, 0.4 maybe, and graph that, here's a new point. Well, by the same logic, we're going to work out which of these is the nearest neighbor. It looks kind of equidistant, but it's probably this one. And that nearest neighbor is blue, which means B, so we'll label this point P. And then, there are ones that are harder to eyeball, like this. So the 0.5, it's a little harder to tell which group it's closer to. But probably if you computed all the distances, there would be one point that would come up as the closest, and that would be the one that you give the label to. So coding this is about getting all of the points and computing basically a big array of distances, computing the distance between the new point that you're trying to classify and all the other points that you know. So it's a kind of a funny learning algorithm in that it doesn't really learn. All it does is you give it a bunch of data that's labeled, and it just remembers that data. And anytime you want to classify something new, you give it a new data point, and it looks at every single thing that it remembers to see which is the closest point to the new thing, and it gives it that label. So it predicts that it'll be that label. So if this is photos of cats are clustering up here in the space, photos of dogs are down here. If it's closer to the cat photos, it'll get the cat label. So that's the basic idea behind it. So how does it work? Well, let's go back to the handout here. So we're going to, there's no real training phase. This is kind of unlike other algorithms that are coming that are more complicated. We give it a whole mess of data that's labeled and say, here you go, just remember that, and it remembers it. And then when a new point comes in, it just has to go through every single example that it knows and compute the distance. And the easiest thing to do is to use the Pythagorean theorem to compute what's known as the Euclidean distance. So we're looking for the distance between 2 points in 2 dimensions. This is the Pythagorean theorem, which just says that the length c is equal to the square root of a squared plus b squared. It comes from this relation here. You take the square root of both sides and you get that. Well, if those are 2 points that you're trying to compute the distance for, this is x1, y1, and this is x2, y2. This length down here, b, is the x distance, the difference between x and y. And this one here is the y distance, the difference between, this is the difference between x1 and x2, and this is the difference between y1 and y2. And it doesn't matter, if you subtract these numbers here, if x1 is smaller, as it is here, this will be a negative number. But that's okay, because when you square it, as you have to do in the Pythagorean theorem, it's going to come out positive. So to figure out the distance here, you just subtract x1 minus x2, y1 minus y2, square them, and take the square root, and that's your distance. So this is the formula that we're going to use, the Euclidean distance for now, using the Pythagorean theorem. And we can visualize it in 2 dimensions, but it also works in 3 dimensions. You can work out the distance between 3-dimensional coordinates with an x and a y and a z, and it works for 4 dimensions and for 10 dimensions and for 100 dimensions. Even though we can't visualize a space of more than 3 dimensions, or if you can, you're smarter than me, or maybe you've experimented with substances more than I have. But yeah, normally we can't visualize that, but the mathematics scales up. So if you have, if we're trying to figure out, if we have, so in this data there are five feature values. They do have to be numeric for this to work. And if we have a new example with its 5 feature values, we can compute, it's like, you think of it as a similarity between each of these examples and the new example by doing the Euclidean distance in 5 dimensions. So that means we just subtract, so if we have our new, I'm going to be able to draw this freehand here. Here's our new example coming in. Whoa, sorry about that. Haven't used this whiteboard very much before, but here's our new example. So it's going to look like this. So there's our example to classify. Sorry about that. So we're going to subtract, this is our first feature. We're going to subtract this feature from that, this from that, this from that, and so on all the way down the line. Square all those differences, add them all up and take the square root, and that'll be the distance array. So we're going to end up with, I don't know if I can easily copy and paste here. Let's try that. I think I've got a lasso select here, so I think I can just do that. I copy it and then paste it. Yes, I can. Look at that. So the idea here is that you will end up with a related array, another related array of distances. So this is our data array. Item 0 is the values for data item 0. Label 0 is the label, and then we'll have a related array of distances. And then we just have to search through that array for the smallest distance. If we find that, say, number 3 is the smallest, then number 3 is the corresponding label that we want. Okay, I hope that was helpful. It's my first experience with Microsoft Whiteboard. So what's good about this? It can be surprisingly accurate. The nearest neighbor classification algorithm, especially when things don't cluster well or when there's multiple clusters for each class. It copes well with outliers as well. So if you have, for example, if you have a red point buried in here somewhere amongst a bunch of greens, it'll generally be okay with that. Most of the classifications out here will still be green because the closest item will still be green. The cons are resource use. So it takes a lot of memory and it takes a lot of processing time to do all those calculations. It has to calculate a distance between each point and every other point. Now the good news from a coding point of view is that in NumPy it's quite easy to do this. So if I go data labels equals create data set like that. Here's my data and here's my labels. Now let's say I have a new data point. New equals, let's do 0.5, 0.5. That should be an NP array, like this. Okay, so I have my data, I have my labels, and I have a new point, 5, 5, and I want to know what label should that point get. So what I want to do is compute the Euclidean distance between this point and all of the points in the array here, like this. And here's something really cool. If I go data minus new, it will broadcast this all the way through. So the first row of this resulting array is the x minus the x and the y minus the y. So it's done what I need to do is this calculation where I subtract the x's from the y's. And it's done that in one step like that. Data minus new subtracts all the x's and all the y's. But I don't just need the differences, I need the squared differences. So that's data minus new squared, like that. So there's all the squared differences. And then I need to add them up. So I can do that by taking the sum, where axis equals, I always get this wrong first try, I think it's axis equals 1. There we go. So I've taken the diff. So if you look at this first row here, 0.9, 0.8, I've subtracted 0.9 minus 0.5 is 0.4, 0.8 minus 0.5 is 0.3. Then I squared those. So I've got x, the difference in x is squared, the difference in y is squared, and then I added them up. 0.16 plus 0.09 is 0.25. And that's happened for all the rows using that new point. So using that one new point in this one step, I've calculated this whole array. Now if I could actually stop there, because I just want to know which is the smallest distance. And I can see right away it's going to be 0.25. What I've done here is I've done part of the calculation. So over here, I've done the x1 minus x2 squared plus y1 minus y2 squared part of the calculation, but I haven't taken the square root. The square root won't change anything important for me. The closest thing will still look the closest, but if I want to, I can do it. I can bracket this whole thing, and the best way to take square root, well, there might be a sqrt method built into, no, there isn't, built into NumPy, but there isn't, so I will just raise it to the power 0.5, because the square root is the same as raised to the power of 0.5. And there it is. Those are my distances. So again, just to remind you, this was my new point. This is my data. This is the distance from each point in the data array to the new point. And we can eyeball this and we can see that the first point is the closest. But if we want to, we can use, once we've done that, we can say d equals that. So there's our distances. We can say, what's the argmin? 0. So then the answer is labels at argmin, at d.argmin. There we go. So 0.5, 0.5, let me run this again, according to our calculations, should be one of the A points, which is, so that means it was closer to this point here than it was to these. That was difficult to eyeball, but that's what our calculation tells us. So take a look at this calculation, because this is the heart of the algorithm. And it doesn't matter whether you have 2 dimensions or 5 dimensions. So if I go data equals np.random.randint, we'll go between 1 and 100, and we will say that we want 100 rows and 10 features in each row. So here's our new data array. Okay, so there are, instead of being just 2 values, an x and a y, there are 10 of them. And so we need a new point. So let's say our new point is equal to np.array 50, 50, 50, 50. How many do we need? 10, I think. 1, 2, 3, 4, 7, 8, 9, 10. Actually, an easier way to do that would have been np new equals 50 times np.ones 10. That would get me 10 50s as well. So then I can use the exact same calculation that I used before. Let me just up arrow through it. D equals data minus new squared. Take the sum along the number 1 axis, so it sums it this way, and then take the square root of the whole thing. And so here's my distances array, my one-dimensional distances array. And then d.argmin. Turns out that item 11 was the closest to our array. Let's take a look at item 11. Yeah, it looks like the numbers here are all close to 50, so it kind of makes sense that it would be closest to our new data point, which was right in the middle at 50, 50, 50. Okay, so that is the power of NumPy and array programming in action there, showing you that calculation. So what I want you guys to do is implement the nearest neighbor algorithm. So what this means is you create a classify method. You pass into it 3 things, the data and the labels. So you'll have to separate the data from the labels, and then you give it a new item. And that new item is going to be essentially the same shape as a row of the data. And then it says for each row in the data, compute the distance between new item and the current row. There's a word missing there. And keep track of the array index for the smallest found so far. Well, that's if you were doing it in Java or something, but we can do this in a couple of lines. We don't have to write the for loop or anything like that. We can do this whole calculation in a couple of lines and use argmin to find the index. And then we just return the label from the labels array. So the idea is that you're able to call classify, give it a new data point, give it the whole data array and the labels array, and it will return the correct classification. And if you want to use, so you can use this data here, create data set to create data and labels, and then that's your first 2 arguments that you pass in. There's also a create data set 2, here, which if I go d comma l equals that. The data is a bit more extensive here. Whoops, not data. I did d comma l. You get a random array in 2 dimensions again, and a set of labels, A and B. And if you want to plot them, you can. This is what they look like. They're kind of an overlapping set of random points, and it's different every time you run it. So if I run it again, I get a different overlapping set of points, but there's an overlap in the middle. So you could use this to test your k-nearest neighbor algorithm. So what you would do for that is you would generate some new points, or maybe take half of the points that are generated here and use them as your new points, and one by one call your classify method to determine what is the label for that point, and then compare it to the answer that you know to be true. Okay, so that's the basic that's the nearest neighbor algorithm, not the k-nearest neighbor algorithm. And what I would do is I would maybe stop here and see if you can write this. This is going to help you. So you write classify, or you can call it whatever you want, just call it nearest neighbor, and see if you can get it to work using the data, just the sample data and sample labels that I gave you. If you use that small data set, if you use create data set 1, then you get a much smaller and more manageable set of data and labels, and you can test, pass it new points. So you'll call it like this, classify, 0.5, comma 0.5, and then the data, and then the labels, like that. And it should come back with the label A. It should return the label A, as we just saw, because that's the correct answer for that. So yeah, so good luck with that. And I would pause the video and you can restart it. We're going to look at expanding this and creating the k-nearest neighbors algorithm. Okay, so let's talk about k-nearest neighbors. So the nearest neighbor algorithm that I showed you is surprisingly powerful and can do really, really well on a lot of different kinds of data sets. It is slow when you have a lot of data, which is its main drawback. It also doesn't give you a theory. A lot of times when we're investigating data and doing machine learning, we want to learn a theory of the data. What makes something a picture of a dog versus a picture of a cat? And this doesn't tell you anything very informative. It just says, well, this picture was closest to a cat picture, so I picked a cat. Versus this picture was closest to a dog picture, so I picked a dog. That's not much of a theory. So that's kind of another knock against it as well. But there's another problem, which is overfitting. So when the data is messy, you can get overfitting. So imagine that if we go back to the this data here, imagine that. So this data is pretty messy already, and it's going to be difficult to find any algorithm that will do well in this area. But suppose there was a red dot out here. Imagine if there was one red dot just sitting by itself way out here in this big area of green. That might be a correct classification, or it might be a mislabeled point. At the very least, it's an outlier. And you probably don't want to categorize things way out here as legal, as counterfeit, sorry, when they're in this sea of legal banknotes. So there might be something important about that data point, or it might be that it's just been mislabeled. There was a mistake in the machine and the scanner. The variance and skewness were measured wrong. Similarly, there could be a green point down here surrounded by red points. And if you just take the nearest neighbor, then if the new point happens to come in closest to that green point that's sitting surrounded by a bunch of red points, it will classify it as green when probably it should have been red, because that outlier may have been a mistake. So that's called overfitting. So you've learned to fit the training data too closely, and you're missing generalizations. So the way around that is to expand our nearest neighbor, which just looks at the closest neighbor, expand it to have voting, to look at the k-nearest neighbors. So if there's just one green point sitting out here, if you look at the 3 nearest neighbors and identify all 3 of the closest points, you're going to find 1 green and 2 red. And then if you let them vote, the reds will outvote the green, and the one outlier will be neutralized. So most people don't use the 1 nearest neighbor algorithm. They use a k-nearest neighbor, where k is typically an odd number, like 3 or 5 or 7. That's in the case that you have two classes. You can break the ties easily if you have an odd number. So people will experiment with different values of k. So the k nearest neighbor algorithm, you can modify your classify method if you wrote it before, your classify function, which simply computes all the distances and then finds the minimum distance and returns the label that goes with that. Now what you need to do is find the k closest items. So once you've got your distance array, so let's get some data again. I'm going to go back and create that big data array that I had before. There it is. Here's our data array. And where's our new that went with that? Nope, that's not it. Here we go. Oh no. Ugh. Okay, there's our new. So we've got data, and we've got our new item here, and we have a distance calculation, which looks like this, which gets us the array of distances. And we found the smallest distance with argmin like that. That gets us the smallest distance. In this case, I created a new array, so the new one apparently that's closest to our new point is this one. But we want to vote now. We don't want to just take the nearest one. We want to take the top 3 or the bottom 3. So what we want to do is we want to sort. So we can go d.sort like that. And now the array is sorted into the smallest distances first, like that. Actually, we don't want to do d.sort. We want to do, where are we? So we'll get the distances, d.argsort, I should have said. Like that. Because we don't want to mess up the association. Remember, we've got our 3 related arrays here, our data, our labels, and our distances. We don't want to mess up the association between the distance array and the label array. So now this is the order from smallest to greatest of distances. So 5 is the closest, then 66, then 30. So if we want to take, say if we're doing 3 nearest neighbor, we can just slice off the top 3. Those are our 3 nearest neighbors. If we're doing 5 nearest neighbor with k equal to 5, we slice off the top 5. And then we can take a look. We don't have the, so you'll have to do a little bit of work here. Actually, you can do this, argsort 5 like that. There you go. That gets you the 5 examples from the data array that correspond to the 5 closest items after we've computed the distances. If you do that, I don't have a labels array, but if you do that in a labels array, you'll get an array containing the labels, and then you can just go through and count the instances of each label. If you have multiple different labels, you might want to use a dictionary to count the votes. So you can create a new dictionary, and every time there's a new, and then go through the array one item at a time, go through the array of labels that you get for the nearest neighbors, and each time there's a new label that you haven't seen before, add it to the dictionary with a value of 1, and if it's already there, increment it. And then at the end, you need to do a little trick, and I'll let you guys do some research on this. You have to figure out how to pull that information out of your dictionary, sort it, and find the item with the highest number of votes. Okay, so that part I'm going to leave for you guys to struggle with, but of course I'm here to help you. So you compute the distances as before. You sort them to find the k closest items to the new item that you had passed in. The new classify method, by the way, requires a k parameter. So new item, data, labels, k. So what I would do is clone this one once it's worked. Once you're reasonably satisfied this is working, clone it, add a parameter, and then change from this part down. You have to write some code to tally up how many of the k nearest neighbors belong to each label, and then find the label that got the most votes and return it. And that's the k nearest neighbor algorithm. And it really does help, and I want to show you, it does help with overfitting sometimes. Sometimes k equals 1 is the best you can do. It depends on the data set. But here is a, piece of code that I wrote. Let me explain it. It produces these graphs. So I'm using the k-nearest neighbor classifier. This is the iris data set from the UCI machine learning repository. We're classifying 3 different species of iris plants, flowers, based on 4 measurements. But again, I've taken 2 measurements so that we can visualize it. When you do it with 2 measurements, you can see it's a pretty hard task. It overlaps a lot. So each different color is a different species of iris. So these are the correct classifications. And then what I've done is I've tested, I think, 100,000 points. I split this up into 100 by 100, and I passed my k-nearest neighbor algorithm every single one of these points, and then to see whether it would classify it as red, blue, or green. And then I plotted them here as pixels, and what you end up with is a really neat picture of how the classifier is dividing up the space. So any point that lands over here is going to get red. Any point that lands out here is going to get green. And you can see when k equals 1, when we're just looking at the nearest neighbor, anywhere there's a little outlier point like this one gets an area around it that will always be classified green. So any point that's closer to green here than any other will get classified. Similarly, we've got these little islands of blue out here. Then with k equals 3, it starts to look a little bit more regular. 7, 11, and finally 15. So here in k equals 15, we're taking the majority vote from the 15 nearest neighbors, and it sort of looks like we're making some generalizations here. We're closing in on a generalization that stuff up here belongs to the red class, stuff down here in this triangle belongs to the blue class, and with a couple of tiny exceptions, stuff over here belongs to the green class. So if this overfitting over here with k equals 1 may lead to a lower performance than a higher k. It may be k equals 3 that leads to the best performance, or it might be one of the higher values. So that's the advantage of increasing your k value. The idea behind all of this is that rather than do an exercise this week, we're devoting all that exercise time to creating a k-nearest neighbor algorithm. So I'll go over some tweaks that you can do to the k-nearest neighbor algorithm in the next video, and then we'll talk about the assignment. And if you followed along and tried this stuff and spent some time trying to work out the k-nearest neighbor algorithm and making it work, then you'll be in good shape for finishing the assignment. So that's it for this video. I have another video on problems with KNN and making it better, and then we'll have the assignment.